Hello, this is the second big video of the breaking in write-up. In the first video we explored how the VM works and how to perform syscalls, and in the mini video in between we automated program assembly. In this video we'll finish the task by using the network syscalls to create a proxy and use it to connect to the SSH server from the inside, thus bypassing the firewall. First of all, I'd like to set up an ngrok tunnel. This gives me a host and port that anyone from the internet can connect to, and that connection will be forwarded to whatever program is listening on port 1234 on my machine. This step would not be necessary if my machine was exposed to the internet, like if I was on a VPS. Another option would be setting up port forwarding, but I think that's overdoing it. We'll start a netcat server on port 1234. The L flag means this is a server. The V flag means we want it to tell us about incoming connections, and the K flag means it won't stop after the first one. Now that we have that out of the way, we can start trying the cool syscalls on the remote VM. The first program I'd like to try just makes a connection to my machine, ends that connection, and then exits. For the time being, we won't send any data, just connect and verify that this crucial part works. To do this, we have to run multiple syscalls. The first one is the socket syscall. It takes in a domain, which is the internet in our case, for which we use af_inet. The second parameter is a type, set to sock_stream, which makes it a TCP socket. The third parameter is called protocol, but we can leave that 0. I'll quickly put these parameters in the program memory and label them socket params. The socket syscall returns a socket file descriptor, which is a number. Each socket has a different file descriptor, so that we can give that to other network syscalls for them to know what socket we're talking about. I'll leave some space for this and label it socket fd. And in the code I'll just do a syscall with the socket syscall number, params at socket params, and return value at socket fd. This socket doesn't do much currently. To actually do anything, it must first connect to some address. For that, we use the connect syscall. Its first parameter is the socket file descriptor we just got earlier. Let's set up a parameter array and leave space for the socket fd. I'll use an add instruction to copy the descriptor over there. The second parameter is a pointer to the socket address, and the third is the length of the socket address. This socket address thing is a structure that specifies what the destination host and port are. Looking through some documentation, we can find that the general case looks like this: 2 bytes for the address family followed by 14 bytes of data. We aren't in the most general case though, so we can look for the sockaddr in structure. This is a version of the structure specialized for internet addresses. We can see that the 14 data bytes are actually made of 2 bytes for the port, 4 bytes for the IP address, and 8 unused bytes. Let's construct this in memory. We'll start by marking its beginning with a label. After this comes a 2-byte number, which is the address family field, which is af_inet. After this comes the port. I won't hardcode any port in and will instead just mark it for formatting. This way we can put any port we want here from Python. After the port we have 4 bytes that are the ngrok IP address. Once again, I'm not hardcoding these. The next 8 bytes are all zeros. Great, the socket address structure is now fully fleshed out. Going back to the connect syscall parameters, we can give it the location of the socket address structure, as well as 16 for the structure length. Let's not forget to call the syscall. We aren't interested in the return value, so I'll create a label at which we can just send all unnecessary junk we encounter. If we would run the program now, we should see a connection being announced by netcat, but let's not do this just yet. Let's first nicely close the socket and exit the VM program. To close the socket, I'll use the close syscall, which takes in the file descriptor of what we want to close. Up to this point we have created a socket, made it connect to our server, and closed it. To finish it all up, we can run the exit syscall. Now to send this, we can read the assembly file we just wrote, replace port and IP with the ngrok port and IP, and compile it. Having assembled it, we can now send it to the server. Keep an eye on the netcat window while I'm running the program. Bam! For a brief moment, we have the connection, which immediately closed. This tells us that the code worked as intended. That's awesome! Now let's make our battle plan. Our proxy will look like this. Initially, it will set up 2 connections, one running in between the VM and the SSH server, we'll call it VM to SSH, and one running in between VM and our machine, which we'll call VM to us. What should happen is that the VM should regularly check if any of the connections have incoming data and forward it to the other one. For example, we might send some data on the VM to us connection. The VM must detect this, get that data, and send it to the VM to SSH connection. Same thing in reverse. There will be 4 parts to this exchange. First, the proxy will get all the data from the VM to SSH connection. Then, it will send that data to the VM to us connection. After that, it will get all data from the VM to us connection, and finally, it will send that to the VM to SSH connection. This will be repeated many times so that we can communicate with the SSH server. Let's implement this. The program will become quite messy towards the end and the screen will be really crowded, but I'll try to focus on small little individual steps to keep it simple. We'll start by creating 2 sockets, VM to SSH and VM to us, just like we did in the last program. After this, we'll connect each of those to their respective endpoint. One of them will be for localhost port 2222, so we can set the IP to 127.0.0.1 and port to 2222, which is 08 AE in hexadecimal. The other will be the same as in the last program, as it just connects to our machine. Now we should have 2 connections. It's time to begin the proxy loop. I'll mark its beginning with a label. As we had discussed earlier, the first step in this loop is getting all the data from the VM to SSH connection. We can use the rec from syscall to do that. Let's set up a parameter array and label it step 1 params. The first receive from parameter is a socket file descriptor. We'll set that using an add instruction as we do not know it at compile time. The next one is a pointer to where the received data should be written. I will leave 64 bytes for an internal buffer called buff. The third param is the length of the buffer, so we'll put 64. The next 3 params are flags, an address and its length. For now, we can set all of these to 0. The receive from syscall's return value tells us how many bytes were read. This is the first step done. Now for the second one, we need to send this data to the VM to us socket. To do this, we'll use the send to syscall. The syntax is pretty much the same as receive from, but now the length parameter isn't the maximum amount of bytes we can receive, it's the actual amount of bytes we want to send, which may be different every time. This is the return value of the receive from syscall, so I'll use the add trick to copy that over here. Now that we have the send to parameters set up, we can actually do the syscall. We're halfway there. Now we can do exactly the same thing, but switch out VM to us and VM to SSH. The loop body is now done. Now let's also jump back to the beginning with the good old subtract trick. Also, before receiving and sending, the parameter lists should have the correct file descriptors in the first position, so let's set those using the add to 0 method. To recap, our program should start by creating 2 sockets and connecting one to the SSH server and one to our server. After that, it will enter the infinite loop in which it receives data from the SSH server and passes it to us, and also does the reverse. Let's try to run it. Pay attention to the netcat window. And we get the beginning of an SSH connection. We can send it the same version string so that it's happy that we match versions. After doing that, we'll receive some SSH data that details the ciphers the server knows about. We can see that we only received the first 64 bytes, as that is the size of our buffer. Currently, the proxy is waiting for our input. I'll just press enter so that we can see the next 64 bytes of the cipher specification. Pressing enter a few times more, we can get the whole cipher spec, but unfortunately, the connection also ends. What happened is that when I pressed enter, the proxy sent that to the SSH server. This is bad, as most probably a whole bunch of new line characters are not what it expected, so it closed the connection. Damn. One way to fix this would be to just make the buffer bigger, but that doesn't really solve the problem. The issue at hand is the fact that the proxy always expects one packet going one way followed by a packet going the other way, and so on. It's just not made for 2 or more packets from the same source one after another. Fortunately, there is a better and more correct way to solve this than just enlarging the buffer. While setting up the receive from parameters, we overlooked the flags, but by looking in the documentation, we can find about message don't wait. This makes it so that the syscall will exit without waiting for input if there is nothing queued up. This is exactly what we need, as there are cases in which we just want to skip a receive step if there's nothing to receive. Let's add the message don't wait flag to the receive from parameters. The spec also says that if there was no data received, it will return -1. This is a slight problem for us as we use the return value as a byte count. Therefore, we need to add a check that only does the send steps if the length is not -1. We can do this like so. First, an is-equal instruction checks if the received size variable has the value -1. If so, the variable check will be set to 1. After this, I'll multiply the check variable by 8 and then add it to the instruction pointer. This weird little snippet pretty much makes it so that if the check was 1, the program will skip 8 bytes, which means 2 instructions. Otherwise, it won't. We can place the send code in these 8 bytes so that it will only be executed if the received size is not -1. After these 2 instructions, we have steps 3 and 4. We can similarly modify them to not send if the received size is -1. Running this, we can notice one major problem. The VM just exits really early with the executed 1 million instructions message. What is going on? The problem with the flag message don't wait is that if there is no incoming data on the socket, it immediately exits. Let's think about this for a moment. We don't really send any data instantly, so before we even have the chance to react, the don't wait exited once and then once more and once more again. It does that really quickly, pretty much immediately wasting all our cycles on useless empty receives. Ideally, we would like something like an if there is no data in the first X seconds exit syscall, but that doesn't really exist. A decent compromise is adding something inside that loop that blocks the execution and unblocks it from time to time, but not often enough that we waste all the cycles. A great option would be a sleep syscall, but we do not have that available. Another option will be waiting for user input on yet another connection that isn't VM to SSH or VM to us. We don't want to send any bad data on those. Fortunately, we have the option of creating another socket to which we can just send irrelevant packets every second or so. Even better, there is a simpler option. As it happens, the receive from syscall doesn't care what kind of file descriptor you give it. It can be a socket, a file, or even something like standard input. This is nice as we can just send it data to standard input through the PoundTools remote object. Remember, up until now we were able to send the program length and its context to standard input, and it most probably hasn't closed this. So the way to slow down the proxy loop is just to add a receive from syscall that reads something from standard input. This way it gets stuck every iteration waiting for some input on standard input. We can send it a message every second or so to unblock the loop for one iteration. Doing this, we will never reach the 1 million instruction limit. Let's set the slowed down syscall's parameters. First of all, the file descriptor is 0 for standard input. The buffer will be buff still and the size 64, but this time no message don't wait flag, so that this one does block. Before going on, let's quickly recap what this big mess of a program does. Over to the left we have a bunch of constants. After that, there's the receive buffer, its length, and the variable check that we use to check if it's -1 or not. Over in the middle pane, we start with the socket parameters. After that comes the file descriptor for the VM to SSH connection, and the parameters that specify the SSH server's address, IP 127.0.0.1 and port 2222. After that, we have the file descriptor for the VM to us connection and its parameters, which are encased within curly brackets so that they'll be replaced by the Python script to whatever is appropriate. After these two addresses, we have the parameter list for the proxy loop, starting with step 1, receiving from VM to SSH, step 2, sending to VM to us, then step 3, receiving from VM to us, and finally, step 4, sending to VM to SSH. In the end, we also have the parameter list for the slowdown receive. Over in the rightmost column, we have label entry, which marks the beginning of the code. The first two syscalls create the sockets. After that, we connect one socket to the SSH server and the other one to us. Before going on to the proxy loop, we must copy the socket file descriptors to the parameter list. So here we do exactly that. Inside the proxy loop, we first receive from the slowdown connection, i.e. standard input. After that, we receive something from the VM to SSH connection, check if the result was -1, and if it wasn't, we send that to the VM to us connection. After that, we do exactly the same thing, but in reverse. Finally, we jump back to the top of the loop. Okay, now that we have all of that sorted out, let's tweak the sending program by adding an infinite loop which just sends short packets and sleeps for a bit. Remember, this is to unblock the proxy loop from time to time. Let's run this. Now in the netcat window, we can see that we received the full cipher spec, not all at once though, but we don't have to send any bad data. We're so close. Currently, we can't really connect with the SSH utility as it expects itself to be the initiator of the connection, not the listener. As it stands now, the network looks something like this. We can see that the VM initiates both connections. As we want something that accepts SSH connections, we can add another proxy-like program on our local machine that accepts both the VM to us connection and the SSH connection and forwards data in between them. I will augment the program we have currently to do this. This can be done quite easily with the listen class from PoundTools. Just create a listener on port 1337 for SSH to connect to and another one on port 1234 for the remote VM to connect to. After sending the proxy to the VM, just wait for both connections to establish. After that, just start a proxy loop that is really similar to what we have on the server. We now have all the puzzle pieces put together. To finish this task, just start the proxy and connect with SSH to localhost port 1337. After just a few seconds, we are asked for the password of user triples. Oops, forgot to specify the username. Let's try again with the correct user, breakingin. We can give it the password hunter2 as the task description told us. And we finally get a shell. ls cat flag done. Wow, this was such a nice challenge. Thanks a lot to my team for covering the other tasks while I spent 24 hours on this one. Also, thanks a lot to the organizers for this wonderfully complex but nicely approachable challenge. And thank you for watching. I've had a lot of fun both solving this and making the write-up. Hope to see you in another one. Bye!